So this will be our third video focusing on the section of Atkins 3b, which is dealing with the entropy changes accompanying specific processes, and we'll be looking specifically at heating in this video. So by the end of this section, we're going to be able to explain in simple terms why heat flows from a hot object to a cold object. So let's start with a derivation. All right, let's start with the definition of entropy, and we're also going to start with the definition of enthalpy. And enthalpy specifically at constant pressure, which we know is going to be equal to the change in heat of a reversible process at constant pressure. So what I can do is then substitute in dq rev p into the definition for entropy, and we can see that the change in entropy is equal to the change in enthalpy at the temperature at which this occurs at constant pressure. So if I substitute in the definition of heat capacity, we know heat capacity by definition is the change in enthalpy per the change in time at constant pressure. Rearrange this equation, so I'm multiplying both sides by dt, so I'm left with dH equals Cp dt. And if I substitute that back into the definition of entropy, I get ds equals Cp dt over T, which is now convenient because, like, if I look here, I have my infinitesimal and a variable in which it can be integrated by. So let's assume heat capacity is constant over the temperature range T1 to T2. So that's usually a reasonable assumption unless we're looking at something very, very large. In that case, we do know that heat capacity does change with temperature, but we're making another assumption that it will be a negligible change. So let's integrate this equation here. So if we take ds and integrate from S1 to S2, and on the right-hand side, we are assuming Cp is constant, so we take it outside of the integrand, and then what we can do is integrate 1 over T dt from T1 to T2. Applying those integrals, we get delta S equals Cp ln, the ratio of T2 over T1. What I can do then is expand the definition of delta S and then rearrange. So delta S, all we know, is going to be T final minus T initial, or delta S is going to be S2 minus S1, or S initial minus S final minus S initial. When we rearrange that, so we have S associated with temperature 2 minus the entropy associated with temperature 1, still equals everything on the right-hand side. And then I can pull that over, and I end up with this equation here. So I can calculate now the entropy of a system at temperature 2 if I knew the entropy at temperature 1 by adding the heat capacity at constant pressure multiplied by the natural log of that change in temperature. So the entropy change associated with the heating at constant pressure. So we have our first equation. Through a similar derivation, we can also derive the equation for entropy change associated with heating at constant volume. It's almost the exact same derivation, which you end up with, instead of dH equals Q at constant pressure, we're going to end up with du equals constant dQ at constant volume. Going through the similar steps, we end up with a similar equation. The only difference is that Cp has now been substituted with Cv, which is the heat capacity at constant volume. So we've arrived at those equations to calculate the entropy change upon heating. So let's see if we can take these equations and then explain why hot objects spontaneously will transfer heat to cold objects. Right? So let's read through this. It says, from the following relationship, we can see that the change in entropy is logarithmically proportional. So delta S sub m, so it's the molar entropy, is proportional to the natural log of the ratio of T2 over T1. Therefore, the increase in entropy of a cold object has a nonlinear relationship with the amount of entropy lost from the hot object it has exchanged heat with. So we're going to see, it's kind of foreshadowing, that the entropy change of the cold object is actually going to be greater than the amount of entropy lost from the hot object donating heat to the cold object. So we have our equation here. And what we can do is start to plot this. So we're going to try to pull apart this figure. Atkins doesn't do a great job of describing it, so I'm going to try to do a better job at that. So what I've done here to make things simple, so we don't have to look at either Cp or Cv, I'm just substituting in the idea of Cm. It's going to stand in for either Cpm or Cvm. And because now we're dealing with Cpm and Cvm, it's basically dividing both sides by n. This equation, which one? Go up. This one, dividing both sides by n, so we get molar amounts of changes in entropy and molar heat capacity, and that's what we see here, right? And so just a reminder, anytime you see subscript m like we do here, it just means the variable in question has been divided by a mole. So it's normalizing it to the amount of substance of the system. And we know entropy has units of joules per Kelvin, and while molar entropy is going to have joules per mole Kelvin. So this is the figure that Atkins has in the book, and what we see here is just different ratios of Cp over over R. And we wonder why he's doing that, right? So if we take a look at the axes, on the y-axis it's plotted, we have essentially molar volume that's delta S over N divided by R, so as we have on our y-axis, right? So if we start with this equation we had here, and we divide both sides by R, what I did is expand delta Sm to delta S over N divided by R. There's the R on this side. Cm and R are actually going to have the same units. They're both in joules per mole Kelvin, and thus it actually just simplifies to a ratio. This fraction here is just a number. So it's a ratio between the heat capacity and R. So effectively what that's doing is acting as the proportion constant between this change here and then this change here. Right? So there's a more evident, it's more clear to see the change in delta S divided by NR and its relationship to the natural log of the ratio of T2 to T1. And that's what we see here. So actually at low temperatures, we can see there's actually going to be a greater change in entropy if Q is added to it than at high temperatures. We have a less steep change. So this is this nonlinear relationship, so that entropy of cold things actually changes faster when Q is dumped into them then the entropy changes for hot objects. So it'd be, say, we go from a hot object and cool it down a little bit, there's a small change in entropy. The same amount of Q is then donated to a cold object. You see there's actually a greater increase in entropy than what was lost from the hot object. So let's take a look at that. Why is that the case? So let's look at a specific example of heat transferred and why it's spontaneous. So what I've done is taken an example of two blocks of iron that I've put in contact with each other. One will be hot and one will be cold. So let's start with the Clausius inequality. So we know for a spontaneous process, the change in entropy total has to be greater than or equal to 0. If it's equal to 0, it's at equilibrium. If it's greater than 0, the process will spontaneously occur. So we can then look at the this equation here where the total change in entropy is just going to be equal to the change in entropy of the hot object plus the change in entropy of the cold object. So this is when we get into our specific example here. So we're going to imagine a scenario in which we place 1 mole of hot iron, let's imagine it's at 300 K, is in contact with 1 mole of cold iron at 200 K. Since we're conducting this experiment in a lab, let's assume this process is happening at constant pressure. That just makes doesn't matter, we just have to pick one of the two scenarios, either constant volume or constant pressure. Constant volume is more common. So since the two pieces of iron are the same material and have the same amount, that means the temperature of the two pieces at equilibrium will literally be the difference between 300 and 200, which is 250. That's the middle point. And just looking a quick search on the internet, the molar heat capacity of iron at constant pressure is 25.09 joules per mole Kelvin. So let's start with our equation here, where we know the molar change in entropy is equal to the molar heat capacity at constant pressure times the natural log of the ratio of the hot object and the cold object. Oh, sorry, that's incorrect. The T2 is the equilibrium temperature, and T1 will be the initial temperature of the hot object. Plugging in our variables, we know the heat capacity of iron. This is the T2, which is the iron has cooled now to thermal equilibrium with the cold iron to 250. It started at 300. So the entropy change of that iron as it donates heat to the cold object is going to be negative 4.57 joules per mole Kelvin. If we switch our perspective and look at the entropy change for the cold iron, same equation. So it has the same heat capacity because we're dealing with 1 mole of iron, and it's dealing with the same heat capacity because it's the same substance. We have our equilibrium temperature of 250 K. We started at 200 K for the cold iron. And so what we see here, the entropy change for the cold iron is actually plus 5.60 joules per mole per Kelvin. We plug that back into the total entropy change of the process. Well, there's our delta S for the hot iron, our delta S for the cold. We add them together, and we actually see the total change in entropy for that process is plus 1.03 joules per mole per Kelvin. And since delta S total is a positive number, it meets the requirements for spontaneity, and therefore the hot iron will spontaneously transfer heat to the cold object until thermal equilibrium is met, right? So once T hot equals T cold, the ratio of T final to T initial for both samples of iron will be equal to 1. And so the natural log of 1 is equal to 0, and if you have that, we have the molar entropy change is equal to 0. That is going to be a system at equilibrium, so there's no longer transfer of heat between the objects when both the hot and the cold iron, those two samples are at the same temperature. There's no more driving force. There's no more change in entropy. They're at thermal equilibrium.